Yeah, lots of laughing. So, because it's a fun exam. That's why I know you're laughing because it's a fun exam. All right, who'd like to start us off with a prayer? No one laughs at that. Thank you, Christine. Amen. Thank you. Michelle, can you start recording? I forgot to record on the Zoom call. Okay, reminder, devotional tomorrow. It's Elder, I don't know how to say his name, Elder Jose Teixeira from Brazil. He's from the presidency of the 70s, so just a reminder to get on and listen. The exam will be next week. It starts on Thursday and goes through the next Monday. So the 18th through the 22nd, I think. There are like 3 practice exams, 3 old exams up that you can use to practice, and there are keys also on Learning Suite. There's a couple of review sheets to help you know what you should know. Yeah, we will have, in the email I sent out, but just really quick, we will have one review day because of the holiday. Is that just next Monday in a week? Yeah, there's no class in a week, but the Tuesday after that is Monday instruction. So we have 2 days in a row where you'll be here Tuesday, which is a Monday instruction, and then Wednesday. We will finish 3.3, which is what the exam goes up through, on Tuesday, and then we will have Wednesday to review. The exam starts Thursday. So it's pretty quick. But at least we get a review day. The other Tuesday, Thursday classes actually don't get any review days. So we're kind of lucky that way. So, all right, any questions before we begin? Okay. Today might be pretty boring until Bart shows up. So let's hope he shows up soon. All right. So this is just an introduction to where we're going in chapter 3. There's tremendous power with algebra. You guys have now been dealing with algebra for years. Some of you maybe a decade, I don't know. It's very powerful that you can represent properties and rules of numbers. There's an example there. You can represent unknowns, and then you can set and solve equations, which is extremely powerful. You can represent formulas and show how quantities are related through functions or other formulas there. And it's also very valuable as a thinking and a reasoning tool, although we're not going to talk about that right now. In chapter 3, we're going to build up these same tools, but for matrices. And it's those same tools you've already learned for numbers. We will use them to represent rules, like that one there. Oh, I forgot the pair of parentheses. Oh, that's bad. Okay, that's a good example for the next slide. We'll use them to represent unknowns and set and solve equations. We'll use them to represent formulas. That formula there, the one with the beta equals x transpose x inverse x transpose y, it's one of the most famous formulas in all of matrix algebra. And they will become a nice thinking tool for us as we go through. But as you probably learned when you were learning algebra, there's a tremendous difficulty with algebra because you have to bring the understanding to the symbols. It's very easy to just go from a plus b squared to a squared plus b squared. Students do all this all the time, even college students. Hopefully you've grown out of that. You can easily write AB equals BA if you're multiplying matrices. That's not true in general. So we have to be careful. Or generalizing the inverses, trying to distribute over multiplication. That's actually, none of these 3 are true. So, but because they work with because these latter two would work with, if they were real numbers, you might start to do that. So we have to be really careful in the rules and the properties. Some of the things with matrices will be familiar and they will work like real numbers. Other things do not. Okay, so just in general, we're moving that direction in chapter 3. We're going to learn a lot about matrix algebra, the operations, how to represent them, how to solve equations, things like that. You had introduced already in 3.1 to some operations like addition, matrix subtraction, matrix multiplication. We're going to spend most of the time on matrix multiplication. We use matrix multiplication a lot more than matrix addition. It's just much more powerful. It's much more complex. It's much more useful. So for most of the rest of the semester, that's what we're going to be dealing with. We rarely add matrices in this class. So brief review of matrix multiplication. I put something like this up on the board the other day. So here in the middle, you've got the system of equations. We learned to augment them to solve them over on the left with row operations. We also could represent them this way, where you factor out an x, y, and z, and then you use these these vector forms to see that we're really finding a linear combination of these vectors that equals the vector on the right. And this is what gives rise, one of the things that gives rise to matrix multiplication. This is a really nice way. It's kind of like our current only way to make sense of matrix multiplication. That is, when we multiply a matrix here times this vector, x, y, z, what we're doing is we're weighting x, y, and z. These are the scalars that we associate with each of these vectors and then add up to get to this last one. Okay, and we don't have to have x, y, z there. It could be a set of numbers. That's just fine. So here the z, the third one down goes with the third vector. The second one down goes with the second vector. First one at the top goes with the first column vector. So, any questions so far? Okay. Okay, here's a somewhat familiar example. This is the peanut butter and bread example where we have, this is first column's peanut butter, second one's bread, top is protein, top is fat, bottom is protein. I think I got all the numbers right. We can use matrix multiplication to take this, this vector 1, 2, that's a serving vector. That means 1 serving of this first column, which is peanut butter. This 2 represents 2 servings of bread. And then we can calculate that this way. That's the same as 1 of the first column plus 2 of the second column. And then we can use what rules we know with vectors and add them up. Here, there's a more complicated version. I'm trying to highlight things here. So you can see the peanut butter and the bread columns. You can see the fat and the protein rows. This is our servings vector here, 1, 2. When we write it this way in the green, you can easily see the peanut butter together and the bread together. 1 serving of peanut butter, and there's our peanut butter nutrition rates. 2 servings of bread serving rates. When we start to combine them this way, down here in the blue, you can see all the fat is lined up and all the protein is lined up. So here you can see the peanut butter and bread. Here you see the fat and the protein. And you add them up and you get total fat and total protein. So, okay, any questions yet? Okay. So the top one here is the one that I just gave to you, what we just walked through. I have a few more here. I've given answers over here to the right. They may or may not be correct. So your task is to, sorry, I'm trying to get this out of the way here. I'll put it at the top. Your task with your neighbors, try to see if they make sense, and if they try to use peanut butter, bread, fat, protein, stuff like that, to see if you can make sense of what each of these could be. Okay? So take a few minutes and work on these.
That would be like if you were trying to like add in a third element like jam or something.
No, I think you can.
Okay, take about 1 more minute. All right. Okay, let's start with the second one. Someone give me a nice food explanation of why it makes sense, why number 2 makes sense. I think you guys all agreed that it did, that I heard. So someone have a nice one, a nice example of what we're doing there. If we can throw on some nutritional facts. Evan? Ethan. Oh, dang.
So the second one, always like you're adding another nutrient.
Okay, so adding in another nutrient, so we could say like fat, protein, and carbs.
And then you can still take one serving peanut butter and 2 slices of bread to figure out how much of each of those is present inside extra carbohydrates.
Yeah, very nice. Yeah, you said we could add on another nutrient, we could pick carbs, and so that you can still think about taking one of the first column, like you still have 1 serving of peanut butter, 2 servings of bread, and it makes sense to add those up. And then you have a total fat, protein, carbs that you get. Very nice. Okay, how about third example? Can someone tell me why this does not work well? Cambria? Okay, third thing you're talking about the 3 down here on the 1, 2, 3. Yeah, so you said that this might be the number of servings of jam, and why is that problematic? That's right. We don't know what the nutritional value of jam is. We don't have any of that data. So it doesn't make sense to take a serving of peanut butter, 2 of bread and 3 of jam, but we don't have jam, so it's like causes us problems here. Okay. All right, how about down here? First, let's start with, does this work or not? Yes? Okay, so yes, it works. Okay, we'll go back in the back with, oh, it's not Christine, but it ends with an INE. Close? IN? YN? What is it? Madeline. Dang it. Okay, Madeline, go ahead. Either way, like you can start with like the size here if you think it works out, or how does this make sense in a food context? Okay, so it's actually the first column. I should not have done a symmetric matrix here. This is my bad for this example, but yeah. So this we're really talking about this one too, and not that one too. So. Oh, fantastic. Okay, very nice. So, so for those that are online, I'm just going to speak through this again with what Madeline said. So we have the 1, 2 here. This we can think about your peanut butter sandwich. So that takes 1 serving of peanut butter, 2 servings of bread. And this we can think about someone else's. So your neighbors. You could also think about it like your breakfast and your lunch, if you wanted to think about it that way, like what you ate for one meal, what you ate for another meal. So any of these contexts is great. And so when we end up over here, we'll end up with a 3x2. Yeah, 3 down, 2 across. And the first column of that will be your nutrition facts, and the second column of that will be the nutrition facts of your neighbor. So fantastic. Any questions about this? All right, so there is a nice rule here about when you can multiply matrices and when you cannot multiply matrices. Someone want to summarize the rule? I know you read about it. Phil? Or Philip? Or Philippe? I'm just kidding. Go ahead. It can have more rows. Oh, no. Oh, you said it can't have more. It actually has to have exact. So yeah, so something has to match up here, and you're right. The rows of the second matrix have to line up, have to have the same number as the columns of the first. So that's exactly right. Yeah. So we could keep adding over here. Like that's fine, right? We could keep adding neighbor. We could have a column for every one of you for your peanut butter sandwich. Okay, that's just fine. This could be really long, this second matrix. We could also keep adding down here. We could keep adding nutritional facts, nutrients for each of these. That's just fine. What we can't do is start adding another food without adding something here. So nice job. Thank you. Yeah, so there's that last one. That's what that should look like. So, okay. I did Alice and Bob, so very similar to what Madeline brought up. I picked 2 people. Where the first column in that 2x2 is the servings for Alice. Here we have servings for Bob. So very nice. Okay. Now, here's a question you may have wondered about. Why didn't we define matrix multiplication having to do with a horizontal or row vector? Seems like it matches up better, right? Then you're like, oh, x to x, y to, x to the first, y to the second, z to the third. You don't have to do this twisting sort of thing, right? Why don't we just do it that way? Wouldn't that have been nice? It's not some historical mistake that they did that. There's actually a very, very good reason. It's going to take us most of the rest of the class to build up to why. but there's a very good reason why we didn't define multiplication this way, and that we actually have to have a column vector here, or think of the columns of the next matrix to match up with the rows of the first matrix. So. All right. Here is here's a vector. All right, let me hide that for a second. That's a vector with a y. Okay, let's just live on the real number line for a second. So ignore that we're on a grid. We're just thinking about the x coordinates here, not worried about y coordinates. So we're going back to like 4th or 5th grade for you. Okay, here's a vector. And if we multiply that vector times 2, what's going to happen? It's going to double in length. It's going to stretch it out, right? You can think about lining up two of those vectors end to end, or you can think about it stretching out, stretching by a factor of 2. And sure enough, if we do 2v, we get 2 of those. Okay. What if I multiply by a -2? It's going to change direction. It's going to go the opposite direction, and it's going to stretch it by, and it's going to increase its length by 2. And I made a mistake there. So -2 times the, and there we go. So it reverses. So when you're dealing with just on the real number line, when you multiply by a scalar, which is the only kind of multiplication you do on the real number line, then it can do 2 things. It can change the length, or it can change the direction. But you only got 2 directions. You can, to the right or to the left. That's it. So, well, let's look and see what happens if we are not just stuck on the number line. So I'm going to pick the vector 1, 3. And if we can still multiply it by a scalar, I can still multiply it by 2. What happens? Same thing, stretches it. Okay, multiply by a -2. It reverses direction. But if I live in R2, if I live in this plane, meaning I could draw V from the origin to anywhere in the plane, I'd like to be able to transform it to get to other places in the plane, not just on that line. If I only multiply by a scalar, I'm only stuck on that line. So let's throw in a matrix here. Oops. Okay, so there's L1. What if I take L1 times my vector V? What's going to happen? Just talk to your neighbor. What do you think is going to happen here? Okay, so I worked it out up here. Started with the vector 1, 3. I multiplied it by this matrix. What did we end up with? 1, 3. What seemed to happen? Nothing. Okay. All right. So, yep, we just get 1, 3 out. But what if I change it to maybe 2001. What happened here? Someone have an idea? Yes. The claim is the X component of it got doubled. Why did you say that? Yeah, but something else could have happened. I mean, like, there's different ways that I could have got to that point. I couldn't have just, may not have just doubled the X coordinate. But there's another reason why. Okay. Yeah, well, so your thinking is right. You doubled the X component. You can see that with the matrix, when you multiply the 2, 0 here times the 1, 3, which we're really doing a dot product here, which is another way to think about this. 2 times the 1, 0 times the 3. We're only working with the X component with this 2, right? So this new value here is going to be 2 times 1, and that 1 came from here. And what happens with the Y component? Nothing. Like the 0 times the 1 and the 1, so we get nothing. The X component doesn't do anything to help with the new Y component. And you get 1 times the 3, which is just the 3. But if you change 1 and 3, to just X and Y, then you'll get 2x plus 0y, 0x plus 1y. And so here you can see at whatever point I get here, I'm going to get out a vector that has twice the x value and the same y value. So, okay. All right. How about this? It's 2003. What do you think happens here? Someone want to raise their hand? Sydney? Double the x value, triple the y value. Yep, very good. We do the same thing that we did on the board. We could put the x and the y there, and you'd have 2 and 3 on the diagonal, and you'd end up with 2x, 3y as your new vector. So very nice. And how about here? Who knows? It's we don't know what the transformation is right off the bat. That's kind of tough to decide. It's going to be some shear thing going on, maybe, I don't know. Okay, so let's get back to some simpler ones. Checking my notes here. What will this do? What if I multiply that 1, 3 vector by 0, 1, 1, 0? Okay, 0, 1, 1, 0. So talk to your neighbor. Think about what will happen with that. Not just where that goes, but what's this transformation doing? Okay. So I've heard, just from sitting up here, I could hear a couple people. You get 3, 1, okay? But there might be lots of different ways we can change this to get to 3, 1. I heard some people say you reflect it along the line y equals x. Why might that be? Well, 0, 1, let's do this with a generic xy. If I have a vector or a point here, how's this going to change it? Well, my new x coordinate will be whatever my old y was. And my new y will be whatever my old x was. So it's going to swap my x and y coordinates. And that's the same as, that's exactly the same as reflecting it across the line y equals x. So instead of going over your x and up your y, you go up your x and over your y. You're up your old x and over your old y. So nice. Okay. Now here's the tough one. Yes, Philip.
I remember back in algebra class, like if you think of this 2 by 1 vector as a straight line with a slope, and wasn't there something like if you take the reciprocal of it, you get a line perpendicular to it?
Yeah, so Philip asked something about, isn't there something about the reciprocal, and if you've got a line and thinking about the slope of this line, isn't there something about taking the reciprocal of that and finding a line perpendicular? Yes, there is, and it is connected here, or can be. So if you have a line y equals mx plus b, the slope of an orthogonal line, a perpendicular line, is a -1 over m. So it's not just the reciprocal, but it's the negative reciprocal. And in terms of vectors, that means, well, I'm going to hold off for just a second. I might be giving too much away with where we're going. So, so now my question for you guys, and Bart's going to show up any minute now. What 2 by 2 matrix could I multiply this by, or any vector by, to rotate it 90 degrees to the left? Okay, so we're 90 degrees to the left. So it's the hardest question so far. Sit down, work. You can do calculations if you want. Talk to your neighbor. What do you think it's going to be?
This, but you just need it like this instead. So this.
let me show you. Wasn't that a funny joke? Okay. Never mind. All right. Let me show you a strategy that you could do to start working on this problem. If you're looking for the entries of a matrix, you could just say, well, let me pick A, B, C, D. I know I have 1, 3. And do you know where 1, 3 is supposed to end up? Yeah, you should be able to think about, hopefully, 1, 2, 3, 1. So I go here, if I go 90 degrees, then that needs to be a -3 and 1. So a -3, 1. Okay? So you could start with this and just start solving systems of equations. The problem is you're going to have 2 equations, 4 unknowns. 1a plus 3b equals a -3, and 1c plus 3d equals 1. So you're not going to be able to solve for all a, b, c, and d. But there's something else you can do. You only moved 1 vector. Pick another vector and do that. Let's just pick maybe 2, 0. Where will 2, 0 go? 0, 2. And then you can do A, B, C, D, multiply it by 2, 0, and you get 0, 2. And then you'll have 2 more equations, and then you'll be able to solve for A, B, C, and D. I didn't see anyone try this. In this particular situation, there's an easy way to think through it, but I just wanted to throw this out as this is like a perfectly nice strategy, especially if you're trying to find something that's more complex. So, okay, so someone that got this, raise your hand and explain to us how you did it. Anyone know that we haven't heard from yet? Come on, who is? Yes, James.
So we're looking for -3, 1, and we ignore the negative, it's just looking 1 and 3. We already know if we take 0, 1, 1, 0, that will do that flip.
Okay, so you think like, oh, well, I know these have, you drew this out and you thought, oh, at least I see that the 1, 3 goes to a 3, 1. This really needs to be negative. But you already know, you do know something about switching things. So maybe you can start with a 0, 1, 1, 0. Okay?
We know that the top row needs to be negative, so we make that top 1 and -1.
Right there? Okay. Does that work out? 1, 3. So yeah, 0 and a -1 dotted with 1 and 3, you get a -3. And then 0, 1, 0 dotted with 1, 3, you get your 1. And boom. And you can check, does it work with 2, 0 and 0, 2? If we had 2, 0 here, you do get a -0 and then just the 2. So you do get 0, 2. Oh, so very nice. Okay. I saw several others of you got that too. Very nice. What do you think should happen? Well, so any questions about this first? Okay, what do you think should happen if I did this? Bart is just about here. I can feel it. What do you think should happen if I do that? And why? Talk to your neighbor. Okay? What do you think should happen if I do this? I heard a couple people say you should end up with a 180-degree turn. 180 to the left or 180 to the right? Yeah, right, doesn't matter. So, but why is the question? You can do the calculation. We could multiply these two. So let's do 0, -1, 1, 0. 0 minus 1, 1, 0. We can multiply these 0. So this is 0, 0. So you get 0 plus a -1, so a -1. Here you get 0, 0. Here you get 0, 0. And here I get a -1, 0. So you do get that. And what happens if you multiply this vector times 1, 3? You just end up with, a -1, -3. Because this is the same as pulling out a -1. And then you have 1, 0, 0, 1, which we found out did nothing. This is called the identity matrix times 1, 3. So in squish down there, it's the same as not changing it and then just multiplying by a -1, which will point it the opposite direction. But there's another reason why. So even if you didn't do the calculation, there might be another reason why you'd say it would be 180 degrees. Someone want to raise their hand and explain why they think that? Yes.
Know that 0, -1, and 0 rotates it by 90 degrees, and so you're doing it twice.
All right, so it seems like it makes sense. You're going to do this transformation twice. In fact, if we multiply this by 1, 3, you do get 90. You get a vector that's been rotated 90 degrees, and then you multiply this by that vector, and you get another 90 degrees, right? So this makes sense that should happen. But this only happens. This is like the key on why we define multiplication, the matrix and vector multiplication the way that we do. Is this only happens if we define matrix multiplication this way. And this makes a lot of sense if you just keep doing this transformation. And so even though it seems odd to have that vector this way and not this way, we get this really nice thing that happens that makes a lot of sense. If we put two of these transformations together, we get that the vector the matrix that represents doing that transformation twice. So even though it'd be nice to have it 1, 3 sideways, because that makes sense, it actually throws off a whole bunch of other stuff. So, yes? Yeah. So is it associative? Yeah, so I'm kind of waving some hands like, shouldn't I have done this first? What about this, right? Turns out it is associative. We can choose, okay? Nice. How about commutative? So we have two vectors here. Oh, come on, Bart. All right, so 0, a -1, 1, 0. 2, 0, 0, 3, or 2, 0, 0, 3, 0, a -1, 1, 0. This was stretch it double in the x direction, 3 times in the y direction. This is rotate it to the left 90 degrees. This was rotate 90 degrees, and then stretch it double in the x direction, 3 times in the y direction. Oops. double in the x direction, 3 times in the y direction. So are those going to be the same? Work it out, okay? All right, has anyone got the first one yet? All right, Sydney, what did you get? Okay, so I'm going to, oh, come on. Okay, 0. And what's, okay? -3. Oh, this isn't working. Okay. 2. Oh. And 0. Okay. So did that do what we thought it would do, Sydney? Yes. What was it supposed to do? Should have stretched it, double it in the x direction, 3 times in the y direction, and then rotate it 90 degrees. Is that what we ended up with? The new BART? Yeah, because we would have doubled to get 4 here, and then you rotate it, you're at 4. Would have tripled to get 9, and then when you rotate it around, it gets 9 there. What about the second one here? Was it the same, first of all? No, it's not the same. So we just learned something really important, that when you're dealing with matrices, A times B is not necessarily the same as B times A. Sometimes they are. If they are, those matrices are called, they said they commute. But in general, AB does not equal BA. Okay? So let's see what happens. See if we can convince ourselves this way. What is, someone tell me what they get for the second one. 0, -2, 3, 0. Okay, was that the same thing we ended up with first time? No. So, because what this did the first transformation, which was rotate to the go to the left 90 degrees, and then it stretched it twice in the x direction. So it went from 3 to 6, because this was 3, so we're down to 3 to 6, and we were at 2 here, and we stretched at 3 in the y. So we didn't end up with the same thing. So, okay, questions? All right, we're out of time. There were a few more things I wanted to get to. You'll have to pick them up from your reading or videos, or I might make another video. We're not starting transformations. There's a whole chapter or section on transformations later, but there are a few things that make a lot more sense if you can think about it in terms of transformations. That's why I introduced this earlier, like why A times B is not the same as B times A. All right, have a great day, you guys. Make sure you look at the homework. You've got 3.2 and the beginning of 3.3. I don't have the reading notes up yet, okay? But I'll be getting those up soon. I'll put them up right after class.
I think they might be on the same